I'm going to move fairly quickly through this, so just stop me if I'm going too fast, okay? Not yet. Don't stop me yet. So what we're going to talk about here...
Why don't we do more?
Well, I'll give you time to do more of these at the end, hopefully, okay? But I want to talk about the electron configuration thing. So what we have been doing, and we actually did this yesterday with phosphorus. I think we used the off-baud diagram you guys had on your notes, and we filled that out for phosphorus, didn't we? Wasn't that the last thing we did yesterday, pretty much? Maybe not the last thing, but we did do that, right?
The last thing we did was that.
Okay, so for phosphorus, well, actually, you know what? It's on here. Never mind. So when you fill out the orbital diagram for phosphorus, it looks like this, okay? That's your orbital diagram for phosphorus. That's an orbital diagram, okay? In other words, it's the diagram where we put the electrons into the orbitals, all right? Just remembered one thing I wanted to show you real quick, because I want you to understand what these letters mean, because we didn't really talk about that yesterday, did we? The S, P, D, and F, okay? They're really just mathematical probabilities is what they are. So it gets really complicated really quickly if I'm not careful with this. What I do want to tell you, first of all, the S, the P, the D, and the F, remember, an orbital is kind of like a room, right? It's a room where the electrons can be. Everybody okay with that? Okay? It's like a hotel room, or it's like this classroom. We know the electrons are in there somewhere. We just don't know exactly where, okay? The letters actually correspond to different shapes. So I want to show you a picture of what the actual rooms look like, okay? So you can see where, you know, just get to know where electrons live a little bit. I think it's nice to know where they live. But I forgot to pull up the diagram, so you're going to have to give me a second here. Okay. See if I can find one that has the shapes of all the orbitals in one, so I can show this to you. Come on. That doesn't seem to be working, so let's try this one. Big X. S orbital. Okay, here we go. All right. So right here, this is an S orbital, okay? The one that's kind of a sphere shape. Now you got to think about these in 3 dimensions, right? Okay, so this is an S orbital, okay? So an electron that's in an S orbital is in a room that kind of looks like this. It's just a sphere, all right? If an electron is in a P orbital, then it looks kind of like this. A lot of times these are called like dumbbell shapes, or, you know, it's a figure 8 or an infinity sign or something like that, okay? These can be turned in 3 different directions. So they've got the X, Y, and the Z axis here. Whoops, where'd it go? Where'd you go? Is it not going to let me draw on it? Might not let me draw on it. Whoa, it won't even let me. No, it really isn't going to let me do it. Okay. Well, I'll just draw it on the board, and you won't be able to see this on the video, unfortunately. But, well, here, I can just draw it on your notes. All right, so your S orbital, now this is not going to be real pretty, okay? But your S orbital, if you have one on the y-axis like this, that's the y-axis. You could also have an S orbital on the x-axis, like, well, now it won't even let me draw this. This is a conspiracy. And then you have to imagine one that comes out from the board and goes into the board on the z-axis, okay? So the reason that you have 3 p orbitals in every energy level is because there's 3 different ways these things can be turned, okay? So one of the p orbitals, for example, like in the 3p orbitals, I don't know. There's something really wrong with this smartboard right now. But one of the things with the p orbitals is they can be turned in 3 different directions. You could have a 3p on the x-axis, 3p on the y-axis, and then 3p on the z-axis coming out and going into the screen. Okay, so that's the p orbitals. The d orbitals. See if I can find a good picture of the d orbitals here. No, the shapes. No, I'm just telling you to tell you basically, so that you understand what we mean when I say S, P, D, and F. Okay. This is the d orbitals. Now notice there are 4 lobes, in the d orbitals. So there are 4 different ways they can be turned, and then there's also this weird shaped one where it looks like a p orbital with a donut around it. Okay. So there are 5 different orientations of the d orbitals. That's why there are 5 boxes for the d's. Okay. Guess how many orientations there are for the f's? 7, right? Because there's 7 boxes there. Okay. So. And I don't even care if you know the shapes for the F's, but I wanted to show you the S, P's, and D's, okay? And all that is, it's a mathematical calculation that is done, and it basically says, okay, this is the shape of the room the electrons can be found in, okay? So that's all that S, P, D, and F really means. Does that make sense? Kind of, hopefully? All right, let me erase this, and we can move on. But I just wanted to show that to you. Now it won't let me erase it even. Wow. Okay. So that's your orbital diagram for phosphorus. Okay. Now, this is nice, but there should be a way to talk about where the electrons are without having to draw this every single time. Okay. And there is a way. It's called electron configurations. Okay. So if we want to write the electron configuration for phosphorus, it's basically just a shortcut. All right? So all we do here, we say, what the heck? How am I going to do this in a way that you can see it on the video? I'm going to have to stop this and restart it, I think. It's going to be the worst video ever. Now. Okay, please work. Why? There we go. The black's not working for some reason. That's weird. Okay, so the oh, I have an idea. I just fixed it. Okay. So there was some dust that got in there. That's what was happening, and it was shorting out the light and making it blink so that it wouldn't write. So, anyway, all right. So because we have 2 electrons in the 1s orbital, we're gonna write 1s2. Okay. Then we have 2 electrons in the 2s orbital, so we'll write 2s2. We have 6 electrons in the 2p orbitals, so then I'm just going to write 2p6. And then we have 2 electrons in the 3s's, 3s2. And then 3 electrons in the 3p's, so I'll just write 3p3. And that's just a shortcut way of writing exactly what we did on this orbital diagram. Does that make sense? It's just right, because you count the number of arrows in each of the different orbitals. Okay, all right. So two electrons in the 1s, 2 electrons in the 2s, 6 electrons in the 2p's total. Okay.
But if you don't have that chart thingy, how do you know?
You're gonna have the chart thingy, so you don't have to worry about that, right? You get that for all your quizzes and tests. So yeah. Yeah, I mean, if you do enough of these electron configurations, you're just gonna, I can look at an element on the periodic table and write it pretty quickly now because I do this all the time. All right. So PD is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 5s2, 4d7. No, 8. No, 8. Sorry. Yeah. So see, I mean, it's just kind of automatic. It may not ever get that automatic for you, but you'll get the hang of this pretty quickly. Now, the nice thing about this, okay, if you write it this way, if you add up all of these exponents right here, that should give you the total number of electrons that that element has, okay? So 2 plus 2 is 4, 4 plus 6 is 10, 12, 15, and if we look on the periodic table, phosphorus has 15, okay? So that's how you write an electron configuration. So you need to understand the difference between an orbital diagram, that's this, right, and an electron configuration, which is this. They both say the same thing, but they're just different ways of writing. They're telling you where the electrons are, okay? So it's telling you, okay, there's 2 electrons in the 1s room, there's 2 electrons in the 2s room, there's 6 electrons in the 2p rooms, there's 2 electrons in the 3s rooms, and there's 3 electrons in the 3p rooms. All right? Okay. Do you have to fill in a blank on that, on your notes? Okay. So this is just kind of restating some of the things that you already know, so that you have it on your notes, okay? Orbitals fill in an order. They go lowest energy to highest energy, so they start at the 1s and they go up because electrons are cheap, right? Adding electrons can change the energy of the orbital, okay? If you have full orbitals, that is the best situation. That's why noble gases are so happy. We talked about that yesterday, okay? Noble gases have completely full orbitals, so that's the best, most stable situation. But half-filled orbitals is also fairly stable, okay? So like with the phosphorus example we just did, all 3 of those 3p orbitals were half-filled, right? So that's fairly stable. So that's kind of the next best situation after having full orbitals, okay? Makes them more stable. And what this can do sometimes is change the order in which they get filled, all right? So you have to watch out for that every once in a while, and I'm going to show you an example of that in just a second. So let's practice writing electron configurations, not orbital diagrams, but electron configurations for a few of these elements here. See how we do on this. Without looking at the diagram, that's a little tricky, okay? You'd have to know the periodic table well enough to be able to do it that way. You can just use your off-bod diagram, okay? So titanium has 22 electrons, okay? Yeah, don't write in the blank one, just use it to help you, okay? So you've got the blank one that I gave you earlier, okay? Now, titanium has 22 electrons. So the first 2 electrons are going to go into which orbital?
1s.
The 1s. So we're going to start this thing by saying 1s2, right? Then what?
2s.
Then the 2s2, okay? Then what?
2p.
Okay, 2p, but 6 electrons can go into the 2p's, right? Then what?
3s.
3s, and 2 electrons can go in there. Then what?
3p.
3p, and again, 6 electrons can go in there. Now let's stop for a second and just see where we are.
8.
We're up to 18, is that right? Okay? So we need to put in 4 more, okay? Where are those last 4 going to go?
4s.
Well, there's going to be 2 that go in the 4s2s, and then what?
3d.
3d, and the last 2 electrons will go into the 3ds. Okay? Now, we don't have to draw the orbital diagram for this one, but I think it might be worthwhile to do that for just one more here. Let me erase this stuff. Whoops, too far. Okay, if we were doing titanium, the orbital diagram would look like this. Notice how I'm filling these in, okay? I'm starting by half filling each of them and then going back at the end. Titanium, okay. So then when you go to the 3Ds, guess where those last 2 electrons go? In different rooms, right? Because these electrons, again, they're a little bit antisocial. So if they can get rooms that cost the same amount, if they can get their own room, they'll take it. Okay? So that's what the orbital diagram would look like for titanium. But that's how we write the electron configuration for titanium. Okay. See, I keep doing this, and then it's there. Vanadium, 23 electrons. Well, okay, this gets a little bit boring, writing this over and over again, doesn't it? So let me show you an even shorter shorthand, okay? Another little trick here. And you can use this if you want. You just have to be careful that you use it correctly. Notice, well, here, let me erase this, and then I can show you on the one that's written up here. This whole thing right here, that's the same as the electron configuration for argon, number 18. Everybody see that? Okay? So what you can do, instead of writing all of this,
AR.
you can put AR in brackets, and that means this. It means 1s2, 2s2, 2p6, 3s2, 3p6. Okay? So you can use, it's called it's called noble gas abbreviation. Okay? So you just pick the last noble gas before the element that you're dealing with, put it in brackets, and then you can start there. Okay? So with argon, the last thing we did was 3p6, so where on our diagram do we now start?
What? You use your gas? Oh, no.
Potassium's not a noble gas, right? Well, okay, I guess you don't really know what the noble gases are yet, unless you remember that from 8th grade, because we haven't talked about that. Yeah, the noble gases, well, see, you got to be careful with the color thing, okay? The noble gases are all in that very last column on the periodic table, on the far right. Okay? Helium, neon, argon, krypton, xenon, radon. Okay? All the way down. We're going to learn about that in a couple of days, actually, where that's the what? Not the, well, UUO, if it actually existed, would be a noble gas. Although at that point, that's heavy enough, it might not be a gas anymore. But they can't actually even make it, so they don't know what it would do, right? So basically, those are the noble gases, okay? That far right column on the periodic table. So you can use those noble gases, only those, to abbreviate, okay? Now, you don't ever have to abbreviate, okay? But if you don't like writing all of this every time, this is a shortcut that you can use, all right? So argon is in brackets, and then we start with what? What's the next room that gets filled after the 3p6? 4s2, right? And then we'd write 4s2, and then this has one more electron than the last one. So what would be the last thing we write here? 3d3. Okay? Is that making sense? Okay. Now see, on this one, they wrote the whole thing out, okay? But again, either one of these answers is acceptable. You can either write the whole thing, or you can put the AR in brackets to represent all of this, and then just write the 4s2, 3.
Wait, did you say it can only be noble gases?
Can only be noble gases.
Only blue.
Well, no. There's some blue over there that aren't noble gases, right? But only the ones in the far right column, the very last column on the periodic table. All right, and then chromium, 24 electrons. Again, using our noble gas abbreviation here, AR, 4s2, 3d4, right? That's what we would expect for chromium, okay? Now here's where it gets a little bit tricky. Remember how I told you that half-filled orbitals are a really good thing? Okay? So let's go back and actually do the orbital diagram for this one.
You said it wasn't a really good thing.
Well, it's a good thing, okay? It's not a really good thing like full orbitals are, but it's a good thing. Yes. Yes. Okay. So if we're doing chromium, we're going to end up with something that looks like this. Takes a long time to draw all these arrows. This is why we do electron configurations. Okay. Look how close that is. It's so close to being half full, right? And that's a good thing, okay? So here's what happens. Every once in a while, when these electrons fill the hotel manager, which I guess is the atom itself in this analogy, comes up to the electrons, and it's like, it comes up to the 4s electron and says, hey, if you're willing to pay just a little bit extra, this hotel's going to be a lot more stable, all right? It's just going to be better for the hotel. And so this electron, every once in a while, will say, okay, you know what? That's barely any extra cost. I get my own room. That's not so bad. And what happens is this 4s electron right here actually jumps up just a little bit in energy to go right there. Okay? Now, is the cost between a 4s and a 3d very much? No, that's a tiny little jump that electron has to make. Okay? But the benefit for the atom is fairly large, because now look at what we've got. Everything's half full. Does that make sense? Okay? So with chromium, this is going to be the actual electron configuration, which is a little bit weird. The way we would write this is you'd have your argon abbreviation. Then it would be 4s1 3d5. And that's why it might be a good idea to use your orbital diagram, because then you can see when those sorts of situations occur. Okay? Now, they do give you a good rule of thumb on the notes. Down towards the very bottom, I think the second bullet from the bottom, it says, remember the exceptions for D4 and D9. So anytime your electron configuration ends in D4 or D9, you should recognize, ooh, that's really close to being full or half full. So then what might happen at that point is one of those s electrons jumps up to a D. Okay? That only happens when you go from an S to a D. This is really important that you understand this. It cannot happen. It cannot go from an S to a P. That's too big of a jump. The electron won't do that, okay? It'll just say, nope, that's too much energy. I can't go from an S to a P. It will only happen from an S to a D because the energy difference is so small, okay? Do you have a question? Yeah. On all the S to Ds, it can do that, yes. It doesn't have to just be the 4s to 3D. It could be the 5s to 4D as well, okay? So you just have to watch out for that exception. Now, there's one other time when this can occur. Oh, sorry. Do you have anything to fill out for that? No, we just talked about that, okay? It's because that gives us two half-filled orbitals, okay? And that's slightly lower in energy, so it's slightly more stable. The same thing applies to copper. So if we're doing copper, okay, copper's electron configuration we would expect to be 4s2 3d9 at the end. But again, for the exact same reason, if one of these s electrons jumps up to the d's, now we've got 4s1 3d10. So now the d's are completely full, and the s's are half full. That's fairly stable, right? Okay? So that's going to be a better electron configuration for copper than the one that we would expect. Okay? So what it's saying is, just remember this, for the D4s and the D9s, you got to watch out for that. Okay? And that's really the only time that happens that you have to worry about. It actually happens with Fs sometimes as well, but you don't have to worry about the F exceptions. Okay? And then, I don't know why this is at the end of the notes, because we've already talked about this a whole bunch. Did you guys get the electron configuration written for copper? Okay. Yeah, we already talked about this too. Okay, so with anything really in the column that's with chromium, so chromium's number 24 up there, anything in that column, MO, molybdenum, W, which is tungsten, any of those will do the exact same thing, okay, because they're all in the same column. Anything in the copper column, copper, silver, gold, any of those will do the same thing where they push an electron up from the S's so that they have full Ds. Okay? All right, and then the Pauli exclusion principle, again, I don't care if you know his name. Basically, Pauli was the one who said the electrons have to have different spins when they're in the same orbital because they can't stand to be in the same place at the same time. I don't know. Okay, does that make sense? I don't think it's all that difficult, really. Okay. Where it gets tricky sometimes is just going through and trying to do all the different electron configurations. So, for tomorrow, and you've got about 10 minutes now, your quiz is going to be over the orbital diagrams and the electron configurations. You're going to need to know how to do both for the quiz, all right? So I already gave you the worksheet on orbital diagrams. I'm going to give you one now on electron configuration, and you can just work on that for the rest of the period. I will post these on Moodle, the answer keys, so that you can study them tonight, and then we'll have a quiz first thing tomorrow, okay? All right.